Solving rational equations. Now, solving rational equations just means that you must find x-intercepts of the rational function. For this example here, we can see we have x minus 2, x minus 3 over x. Now, the numerator is going to give us our x-intercepts, always. So at the top, we can see x minus 2 and x minus 3. Setting both equal to 0, we can see we get x-intercepts of 2 and an x-intercept of 3, which gives us our points for the graph. On the bottom where the denominator, we can see we have a restriction of x, and this just means that our vertical asymptote will be the y-axis since x can't equal to 0. This also gives us our domain of the function, which is xcr x can equal to 0. And putting this all into a graph, we can see how we can see how this works out. Look at the graph. It pretty much supports our results from analyzing the equation from earlier. Notice how the graph gets really close to the y-axis, but it never crosses it, always hugging it and going up. And we can see that if we zoomed in here on the point above the line, we will be able to see the x-intercepts, which cannot be seen in this in right now because we've zoomed out to show the different to show the shape of the graph. You can put this into decimals and you will be able to see the x-intercepts. Now, sometimes you won't always get like an ideal situation, and you'll have a factor that's the same on the top and the same on the bottom, which usually means that the y-intercept at that point will equal 0. In this example, we can see x minus 2 and x minus 3 over x minus 3. Now, to solve this, we just must cancel out. Gives us our x minus 2, which means our x-intercept will only be 2. And on the bottom, since we have no more vertical asymptotes, our domain will just be xcr, which means this will just be a linear function. And looking at the graph, we can see it pretty much confirms our results, as this is just a common linear function, which came from our x minus 2 from earlier. And zooming in on the point the y point at 3, we can see that we have an undefined value, which came from our canceling out, which is our hole on the graph. Now we'll be using various tools. Now there are various tools you can use to solve for x-intercepts of the numerator, but we'll be mainly concentrating on using synthetic division, long division, and factoring. Let's do this practice. So we can see in our first one we have 3 over x plus 9 and we have 2 over x plus 5. Now we can't subtract and add values just yet. So we must make sure so we should instead make sure that they are a common base. On the top, we can see 3, and we can see that this is over x plus 9. We can do times both by x plus 5, so we can add and subtract values at the top. So we see 3 times x plus 5, and to make this common, we times both by x plus 9. And we can see we get 2 times x plus 9. And this gives us our values of 3x plus 15 and 2x plus 18. Now by just moving over now we just move over the right side to the left side to get our results. We can see that this yields us a x value of x equals 3, since it's just 3x minus 2x, which is x, and it's 15 minus 18, which is x minus 3. And moving a minus 3 over, we get x equals 3. So that's the solution to our first equation. On the second one, we can see something much more complicated. We see 1 minus 3 over x plus 1 equals 3 over x squared plus x. Now, first step, we must make sure it's common base on this side. So doing this, we just do, so to make this common, we just times 1 by x plus 1, which is just x plus 1. So we get x plus 1 minus 3 over x plus 1, since they both now share a denominator of x plus 1. And on the other side, we don't change anything just yet since we haven't gotten to that part. Now, combining these values together, we get x minus 2, which came from our positive 1 and negative 3. Now, after having our x minus 2 over x plus 1, we do common base again, so we can add and subtract values. So on this side, we do x minus 2 times x squared plus x, since x squared plus x is on the bottom. And on this other side, we do 3 times x plus 1, since this x plus 1 here, which gives us this mess of values that we must combine in order to make a proper function. And we can see that we get x cubed minus x squared minus 2x. And on the other side, we get 3x plus 3. Rearranging these values and adding them up, we get x cubed minus x squared minus 5x minus 3. Now this resembles something similar, doesn't it? This resembles something familiar, doesn't it? It's synthetic division and long division, and we can also see that we have x cubed and minus 3 on the last term. This means we can use b over a and b values. So on our b value, we can see we have -3, and our a value is 1, which means we can just use values of the 1, -1, 3, and -3. And we can use remainder theorem to test out which values equal 0. Now, using remainder theorem, you'll be able to come to the conclusion that -1 and 3 would give you values of 0, and which you can test out yourself. And this means do is just x plus 1, x minus 3 over x squared, over just x times x plus 1 over, no, x times x plus 1 squared, which came from us factoring out the x from earlier, since it's x squared plus x. Now we can see that we have in common an x plus 1 on the top and x plus 1 on the bottom, which means we just cancel these two, which means that we will not have an x-intercept of -1 since we cross that out, which means we will just have x minus 3 over x as our value. Practical uses. Solving rational functions has many practical uses. It's used by businesses to find out whether profits are break even, which aids businesses in planning ahead and making important decisions. It's also used to model the concentrations of medications in the patients over time until the drug leaves the body or it dissipates after being absorbed into the blood. It's also used in physics to simulate different forces acting on an object, such as the tension acting on a beam, with the intercepts being used to represent areas where the stress is 0. Thank you for watching.